Welcome to Calculus 2. We're continuing in Chapter 10, and we're going to move on to series. There was some information I know in 10.1 I skipped that dealt with series, as I was saving it for now. We focused on sequences, which was just a set of numbers, and talked about convergence and divergence within those sequences. So we're moving on to series, which I think you figured out by now is very generally just the sum of a sequence. Right? It is, in the most general term, a sum of a sequence. We're going to, throughout this chapter, just deal with some very specific types of series. So what do we mean by a sum? So if we start with our initial, right, we have our second term, third, and so on, and we add them up. That's what we're taking. Where a sequence was a listing of those terms. So a sequence is a listing, and a series is when you sum them. And we will be utilizing, obviously, the summation notation. So we would say we could sum a to the n. Remember, you have to define where n is starting, and this is where you define it in a series. So we can start from 0, and we will mostly be working with infinite series, and we'll talk about that in a second, which just simply means a sub 0 plus a sub 1 plus a sub 2 plus a sub 3, so on and so on and so on. And we're going to look at what happens here. Now, again, we will be focusing on infinite, but a finite series, of course, that n value is going to have a starting point, whatever that starting point is, but it will have an actual ending point. So then it will be a sub I plus a sub I plus 1 plus sub I plus 2 dot dot dot. We'll do a sub j minus 1 plus a sub j, and I'll end with a sub j. So if you were doing a finite series, well, they're not very exciting because number one, finite series always converge. Meaning they will always add to a finite value. So again, kind of boring, but we will work with infinite. Which I have, of course, already posted up here. That's your infinite series. Now, infinite series, and we will utilize what we learned with sequences to determine this, but an infinite series, as n goes from 0 to infinity, of a to the m, will either converge or diverge. Okay? That will depend on kind of what, very much on what's happening with the sequence of its partial sums. Let's talk for a minute about the convergence, because a lot of the things you're going to learn throughout this whole chapter and these tests that you're going to be given for different types of series will really focus on how to determine if a particular type of series converges or diverges. What is a test for convergence? What is a test for divergence? So convergence of infinite series. So your series a to n, and n goes from 0 to infinity. An infinite series converges if, and this is where we'll use sequences, the sequence of partial sums converges. So if the sequence of partial sums converges, then the series converges. I think the best way to talk about these partial sums is to do it with a rather simple, but it kind of makes sense, series. So let's suppose my series was simply what we would call the expansion of the number 1. So what do I mean by that? Well, what if I took 9/10 and added it to 9/100 and added it to 9/1000 and added that to 9/10,000, and you get the idea. So on and so on and so on and so on and so on. Because one thing tend to have an issue with is, well, how can I add up infinitely many numbers and it converge into a particular value? I think you can see with this particular series right here, if I add up infinitely many numbers, you're going to converge, right? And you're going to approach the number 1. But what is a partial sum? So let's talk about the partial sums for a minute. So if I let s sub n just be the first n terms, s sub 1 is just 0.9, right? First term. S sub 2, 0.9 plus 0.09, right? S sub 3, okay, you get the idea. These are the first 4 partial sums. So if we let S1, S2, S3, and S4 all the way, in fact, I only wrote up to S4, but we're going to go all the way to infinity. Or n, we'll go all the way to n, not infinity. Form the sequence S sub n, then this sequence is a sequence of partial sums. So remember, it's a sequence. You're not adding them up. So the first is 0.9, then 0.99. The second is point. So the sequence looks like this. It's just a listing of numbers. Dot, dot, dot. And the sequence goes on. So the idea is that if the sequence of partial sums converges, then the series of adding them up converges. Because the partial sum, as n gets bigger and bigger and bigger, becomes the actual series, this sequence of partial sums. So for a sequence, we need that general nth term, and that is actually going to be right. So a to the n, or s to the n, I guess we'll call it s to the n, 9 times, whoops, 0.1 to the kth power. Okay. Or n, sorry. So the limit s sub n as n goes to infinity and I want to take the summation of those partial sums but I want to take it as we go to infinity. So the limit is just as n goes to infinity is the summation k equaling 1 to infinity, and get rid of the limit. And we can see it and see that it equals 1. And it becomes the limit of the sequence of those partial sums. Now, if that sequence of partial sums diverges, your series diverges. If the sequence of partial sums converges, your series converges. So it's always kind of going to be important to get that general right equation. So I want to get started working with our first big type of series we're going to work with, and that is the geometric series. And ultimately, the geometric series test. But before we get into the test, let's talk about what the geometric series is. So a lot of the sequences we dealt with in that first video were sequences where you added one term to the next to get the next term. You added something, be it a single value where you had an arithmetic, or we dealt with a quadratic where you had to do the first level of differences was not constant. If the first level of differences is constant, you have an arithmetic, and then you move on to a quadratic, or if you have to get to the third level, you have a cubic. So we dealt with different kinds of ones, but in each of those you were adding. A geometric series has the property that each term is obtained by multiplying the previous term by a fixed constant called a ratio. So in an geometric, we deal with, number one, multiplication to get to the next term, and multiplication of some sort of ratio. So we have summation. Let's go 0 to infinity of a r to the n. So your a value can be any value except 0, of course. A can't be 0 because you wouldn't have a you wouldn't have anything at that point if a were 0. And r is your ratio. Now, the ratio is your fraction. What are you multiplying it by? And then the power is the position. So it's r to the first, then r to the second, then r to the third, and so on, and so on, and so on. So for example, we can have a very simple one, summation n equals 0 to infinity of 5 to the n. So my a is 1. I like to worry about that. My ratio is 5, and what does that sequence, series, sorry. What does that series look like? So it's going to be 5 to the 0, 1, which is 1, right? Plus 5 plus 5 squared, 25, cubed, 125, and so on and so on. Okay. Now, that would look very different than, again, 5 to, or not 5, let's do 1/5. Wouldn't you agree? Because then our series will be to the 0 power is 1 plus 1/5 plus 1/5 then squared plus 1/25. All right. So there's a big difference in what's going to happen with your geometric series if your r is greater than 1 or less than 1. So for example, so we can complete this by stating if r is less than 1, we'll actually expand it to the negatives as well. So basically we want r between -1 and 1. In other words, it's a fraction. So if r, and that's what's happening in this example here, then your series will end up converging. But if r is greater than or equal to 1, or r is less than or equal to -1, it's going to diverge to positive infinity or negative infinity. And you can kind of see that with these two particular problems. So that's the first thing to kind of keep in mind as you're going through these geometric series, whether r is between -1 and 1 or less than -1 or greater than -1. It's going to make a big difference. So for example, let's take a look at another one. Do the summation 0 to infinity of 4 over 3 to the n. So be careful. It is only the third that's being raised to the n power. So in this particular problem, we actually have an a. We have a equal to 4. Your r is a third, right? So that series is definitely going to converge. You've got to be able to look at it and pull out what your r value is if you're simply asked to converge or diverge. We don't know yet what it's going to converge to. We'll work on that and see if we can come up with those partial sums. You can look at another one to see if you can determine if it converges or diverges. This one will be a little more complicated. And you're thinking, what even makes that a geometric, right? Well, can't we break it up, right? So this is where your algebra comes in. Wouldn't that be the summation of 3n over 5n? Summations you can also break up. Just like limits, they follow the same properties. Summation 4n over 5n from, again, I'm going to just do 0 to infinity. All right. So hold on, before you think there's an a or anything like that, isn't that just 3/5 to the n? And isn't this one 4/5 to the n? So that's going to converge, so it converges. If you recall from our improper integrals. If one piece is diverging to infinity, it doesn't matter what the other piece does. That's going to diverge as well. But this one, clearly, they both converge. So the whole thing is going to converge. The question becomes, can we compute what it is converging to? So let's just go back to see what we've done so far. We have done our very first test. Our very first convergence test, and it was for geometric series. All right. And if you don't like to write all that out, that's, let's see. Here, I'll make this a little clearer. We can use absolute value, right? It converges if the absolute value of r is less than 1. How's that? And if it diverges if the absolute value of r is greater than or equal to 1. So here's the deal. This is really just your first test for series convergence. You will have about 6 or 7 of these tests. So you want to, and I will provide, I'll put it in the modules, a set of the tests so that you can kind of take a look at them and you have them all together when you're studying. You cannot use them on the test. You have to know them for the test. So the first one, the geometric series test, if that ratio, the absolute value is less than 1, it converges, greater than 1, it diverges. The very first test. Get that one memorized and you'll be partway there. All right, but knowing converging or diverging doesn't, it's good, but let's see if we can get some more information to see if we can actually compute what that sum is. Since we know the sum isn't going to infinity, we can compute what it is. Fortunately, for a geometric series, there is a formula. These are stuff that you probably came across in middle school at some point, I would think. Maybe you might remember them. But we do have a formula. So if a geometric series converges, we can compute the sum by simply using a over 1 minus r. So we have a nice formula to compute the sum. And remember, this is only going to be used if it converges, so it's only going to be used when that ratio is between -1 and 1, or the absolute value is less than 1. So let's take a look at an example. Let's go from 0 to infinity of 1/2 n. We have a nice geometric series here. Get used to the series, because when we start throwing more in, to use these tests, you're going to have to identify what kind of series you have. So that's something you'll have to pay attention to as we go through these sections. We have a ratio raised to a power. A is simply 1. R is 1/2. Clearly, between -1 and 1, we know it converges. So it converges to 2, meaning the sum of that infinite series is 2. And again, if you're not understanding how the sum of an infinite series can be a single value, just kind of go back to 0.9 plus 0.09 plus 0.099 and so on and so on. This one is also kind of illustrated nicely with a square. So if you take a look at the series, right, what is it going to look like? So the series looks like your first term is 1, right, plus 1/2, plus 1/4, plus 1/8. You're just multiplying each term by a half, plus 1/16. You know, so if you think of the 1 as a perfect square, right? That's the whole square, so we're good there. Plus, now I want half a square. Well, that's only half a square. Then I want a quarter of a square. Well, there's a quarter of a square. Then I want an eighth of a square. Well, there's an eighth of a square. Then I want a 16th of a square. Well, there's a 16th of a square. That will keep getting smaller and smaller, but you'll keep digging into it. So at the end, you get 2 whole squares. So it does, you know, just kind of nice to see a visual of why that goes to 2. All right, let's keep going. Next one, let's take the summation. Just go through a couple examples. So R equals a fourth. Get that out of the way first. Converges, we're good. Now here's my problem. Do you see the problem? For us to use our summation formula, by definition, our geometric series is the summation n equaling 0 to infinity. Yeah, that's not 0 to infinity, correct? So the question becomes, how can I change that? And, you know, hopefully you're thinking some sort of substitution, right? I need this to go to 0. So I got to take 2 away from that, right? Does that make sense? So I'm going to let n minus 2 equals 0. I'm just going to take 2 away from both sides. I'm going to let n minus 2 equal k. So k is my first term now. So keep in mind, if n minus 2 equals k, n equals k plus 2. What that allows me to then do is rewrite it. Instead of n equals 2, I can now say, hey, but k equals 0 of 3 to the 1/4, but I can't put my n up here, because what does n equal? Oh, n equals k plus 2. Well, that still doesn't help me, right? So now we got to apply some algebra. And understanding your rules for exponents is going to be very helpful. Because recall, right? X to the 5th can be written as x3 plus 2, which is x3 times x2, right? Don't they all be the same thing? Because you add your exponents when you multiply your bases together. So we're going to kind of undo this addition of exponents here, right? So I have summation k equaling 0 to infinity of 3 times 1/4. I'm going to put this squared first. So do you see what's happening? You need to take out the part that's going to get absorbed into your a value. And you get a new a value. We didn't change our r. Our ratio stayed the same. What we changed when we went from n equaling 2 to k equaling 0 is we just changed our a value. That's it. So that's going to give me now, let's see, summation k equaling 0 to infinity of 3/16, 1/4 k. Now it is in a format because what did I need? I need this to be 0. And I need that just to be k. It can't be k plus 2. So once you do the little rearranging there, my a is 3/16, my r is 1/4, and that is all you need for summation. I mean, that and a little bit of arithmetic, right? So it's at 3/16 over 3/4. Multiply by 16 over 16 gives me 3/12, which is 1/4. Yeah, this actually sums to 1/4, and that is just a coincidence. The r being 1/4, coincidence that it sums to 1/4. Okay, so that's how you're going to work with your geometric series. So in this section, we're going to check off one more test for series. We're going to talk about the telescoping series. So this one is a little bit more complicated than your geometric, but it's not too bad. None of them are too bad. What's nice, and what was really nice about the geometric is the fact that it had this formula that we can come up with to find what value it converges to. That part was incredibly useful. And not many series do you get that formula. But one other series where you can do it is the telescoping? No, telescoping. Is the telescoping series. So this one is defined as the summation of n equaling 0 to infinity of b to the n plus 1 minus b to the n. So you can see in a telescoping series, we're taking the difference between two consecutive terms of the series. The best way to kind of look at this one, I'm sorry, I froze for a second, is to just play one out, and you'll kind of see what happens. And what's going to happen is, as you repeat it, a lot of the terms will cancel away. So again, best way to do is just start with a series. So let's do we're actually going to go 3 to infinity of 1 over k is 1 over k plus 2. Okay, let's see what this actually looks like. In other words, let's just start putting some numbers in, and then we'll get a better idea. All right, so for the first set, we're going to plug in 3. That's going to be 1/3 minus 1 over 5, correct? And you're going to add that, plug in the next number. So it would be 4. 1/4 minus 4 plus 2, 6. Keep doing that until you see, I'm going to shrink it down a little bit so I can fit more on the screen, until you see a pattern. And hopefully you'll start to see it. So let me help us out here. This was when k equaling 3, 4, All right, so hopefully you're starting to see what's happening here. So we have 1/6 minus 1/8 plus 1/7 minus 1/9. I'm going to put some dots here. Let me finish what we have. This is k equaling 6, k equaling 7. And I'm hoping you're starting to see what's going to happen, but let some general terms in. So what I mean by that is we're just going to put some terms that, like middle terms, just to kind of get a general idea. So I'm going to call this one I'm going to put in 3 terms. I'm going to do k equaling, I'm going to put in a couple terms, k equaling m. So then I need a k equaling m minus 1 term, k equaling m minus 2, k equaling m minus 3. All right, so I'm using that pattern to kind of do this part. So this would be 1 over m minus 3 minus 1 over m minus 3 plus 2 is minus 1. Okay. We're just plugging back into the original problem up here. So 1 over m minus 2 plus, oh, sorry, minus, one thing. So it's m minus 2 plus 2 is just m. 1 over m minus 1 minus 1, m minus 1 plus 2 is m plus 1. Plus 2. So I did it until I got back to what kind of, right, looks like the original there. To get what I wanted to do here was to get that more general term. Okay, so yeah, show me what's happening. You tell me. Well, 1/5 cancels with 1/5, right? 1/6 cancels with 1/6. 1/7 cancels with 1/7. Correct. And as this were to continue, you can imagine 1/8 canceling, 1/9 canceling, correct? So what do we really have? We have a 1/3 and a 1/4. And when we look at these, what cancels away? So the m minus 3 is going to cancel with a previous m minus 3. M minus 1 is going to cancel. M minus 2 is going to cancel with the previous m minus 2. Your n's are going to cancel, right? Because take a look here. The first thing that canceled, it took us 1, 2, 3 times to get there. The 1/5 canceled 2 prior to it. So that first term is going to cancel with something 2 prior to it. This is going to cancel with something 2 prior to it. The same way this canceled with a term 2 prior to it. Right? This canceled with a term 2 prior to it. So what do we have left? So here's the deal. We got to think about what we got left here. So what we have is our, I'll do it in green, our 1/3, our 1/4, and we have these general terms, right, that we need to use. All right. So it's going to end up equaling 1/3 plus 1/4. So what are we going to do with those? Well, we can need to take the limit of that. right? Plus the limit as m goes to infinity, because remember, this is continuing. This is going to go off into infinity. And what do we have? We have a negative 1 over m plus 1 minus 1 over m plus 2. Well, here's what's kind of nice. Okay, you know your limits. You plug in infinity, 1 over infinity. Well, that's just going to go to 0. And that's just going to go to 0. So all you have left were those two first terms that didn't end up canceling. 1/3, that's 4/12 plus 3/12, and it's 7/12. So we're gonna go through a couple of these since I get my computer not to freeze up again. Oh no. There it is. All right, we're gonna go through another one, and then hopefully you can kind of come up with what's happening here. Now, I started that one at 3. Let's do one that starts at 1, actually. Okay, so when you look at this at first, you're not recognizing a telescoping series, but we can break it up. And this is stuff you learned in the last chapter with integrals, even though we're not doing an integration problem. How do I take this and break it up into separate fractions? Because with our telescoping series, that's what we need, right? We need these separate terms. So, I can do a partial fraction decomposition. I'm not going to go through the whole process with you, but you get the idea, right? Let's see. I'm going to do it very quickly. You end up with, I'll leave the work to you guys. I think you end up with a to the n plus 2a plus bn equals 6. So a plus b, which are your coefficients of n, go to 0 because we only have a 6 in the numerator, so we only have the constant. The constant is 2a. Yeah, equals 6. So clearly see a is 3 and b is -3. So that was a really quick partial fraction decomposition, which allows me then to write this as 3 over n minus 3 over n plus 2. And then that allows me to kind of work out. Now with these telescoping series, really, you really just need to work the whole thing. You kind of have to put the terms together and see what you got. So we're starting at 1. So let's see what happens because we started at 1. You just start writing them out. So the first term is going to occur when n equals 1. Then we'll do when n equals 2, n equals 3. I don't know, we should be able to just do it to n equals 4 at first. So 1, what do we get? We get 3 over 1 minus 3 over 3 plus n equals 2 is 3 over 2 minus 3/4 plus n equals 3 plus dot dot dot. And then you do the n equals m term and the 3 backwards. So you do n equals m, n equals m minus 1, n equals m minus 2. So you have to do those terms. So n minus 3 is 3 over n minus 3 minus 3. Minus 3 plus 2 is n minus 1, m minus 1, and 3, m minus 2 again. Minus 2 plus 2 is just m. Plus, for this one, we have 3 over m minus 1. Okay, now the fun part. Let's cancel. So 3's cancel. Right? 3/4 cancel. Right? So you have to go 2 forward to get the 3 over 3 to cancel. The 3 over 5th will end up canceling. So anything moving forward is going to cancel. What do we have left in the beginning? These two. Okay. What cancels here? Same idea. You're always going to have, this term, right? And because that one's gone, you're going to have this one. I'll put them in yellow. So write out what you have left. Limit. So we have negative 3 over m plus 1 minus 3 over m plus 2. 0. 0. And you have 3 plus 3 halves is 6 halves plus 3 halves, 9 halves. So your test for convergence in this case just comes from if the limit as n goes to infinity of b to the n exists, then you converge. So the limit exists because as you take n to infinity, your limit's going to go to 0. So this limit did exist. And then you can kind of see it's pretty intuitive, get that actual sum and to see what it converges to, because so many of your terms are going to cancel away. There is a general formula which tends to work in certain cases, but we'll the best thing to do with your telescoping, because there's so many different variations, just to start to put out some of the terms. You're really only looking for those first two terms again, those terms that don't cancel, and then the however many terms on this end don't cancel, you're going to end up with the same amount. You just need to double check that the limit, what the limit of that is, because your summation is going to be, you can see everything that doesn't cancel. In this case, it was 2 terms in the beginning and 2 terms at the end. And you know you can come up with that sum. But convergence, as long as the limit of b to the n exists, then you know you have a converging telescopic series and you can come up with that summation.